Welcome, everyone. So we are starting a little bit late. This is 8-1, volume using the calculus. It's a beautiful topic. We started out with a square-based pyramid that was 3 meters on each side and had a height of 3 meters. We used good old-fashioned geometry, and we said volume equals 1/3 big B, which is area of the base, times height. Jeremy said it's units cubed, and in this case, that's right. So it would be 1/3 area of the base is 9 times 3 is the height, which would come out to 9 meters cubed. And Jeremy's right. So then we said, but wait, let's turn our pyramid on its side, run an axis through it, call this an x-axis, call this a y-axis, and then let's take a slice out of that. That would be 3 by 3, even though it doesn't look it. And it would be some x distance away. So if this slice here is some x distance along the axis, what is the length of each side of that slice? What's the length of each side of the slice then? No, we don't know. It's 3 way out here at the end. But remember, this thing starts out here at 0 meters, and it gets bigger and bigger and bigger along as it slides along the x-axis. So what's the length here at distance x from the origin? This is a simple question. Colton, what do you got? Greater than 0, less than 3. Remember, it's x units from the origin, so how long is each side in this case? Right. Well, keep in mind that the biggest each side can get is 3, right? And the height of this pyramid, measured perpendicular to the base, is also 3. So we were just talking in geometry today about similar triangles. These would be similar pyramids. If I drew a similar pyramid somewhere along here, like this, at a distance x from the apex, how long would each side be? Oh, you're working too hard, dude. Normally you're right, Jeremy. But in this case, it's much simpler than that. It's x. There you go. If it's x units from the apex, then each side is going to be x. And Jeremy, what you said is so right. And we'll get into a lot of problems that will be expressed as 3 minus x. But this particular one, since it's day 1, example 1, it's just x. Okay? So this is x and x and x. Everything's x. Okay? So, how cool is that? So here's our slice. Now let's give it an area we'll call a of x. Okay? Good. So it has some area a of x, and it will have some thickness, some infinitesimally small thickness. How thick is it? dx. dx. Okay? dx is a thickness, but it's a really, 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 really small thickness. Okay? So the volume of this slice here, volume of the slice would be what? Oh, you're working too hard. A of x dx. Okay? Now the volume, let's say the sum of all the volume of slices. Okay, if we took a whole bunch of these slices and stacked them up side by side, what would that volume be? equals the integral. Remember the antiderivative, the indefinite integral sign means it comes from the summation. So it's the sum of all those little slices stacked up as they get bigger and bigger and bigger across the way. And I'll pull up calculus in motion in a minute and show you that. So the integral of what? Of ax dx. And from A to B, if A is here and B is out here somewhere. How sweet is that? This is powerful stuff. I can tell you're thrilled. Johnny. You do not in this case. That's a great question. It's a great question. In this case, you don't, because all you got to think about is, can I express the area of that slice? Area first, in terms of just one axis. I can. Why? The area of that little square. Because the sides are all the same. I can express it just in terms of x, so I don't need a z-axis. And that's a really good question. We want to express everything in terms of one variable if possible. Okay? It's a great question. Sometimes we're going to have to work really hard to get rid of that y or get rid of that z and do everything in terms of x, but we really need to. Alex? Well, not necessarily. We would have to manipulate it so that we could express it in terms of x or y only. That's the thing. You know, but we would have to consider that the sides are different and relate them to each other somehow. That's good. Okay, so we know that the area of that square is a of x. We know the thickness of that slice then is dx. And so the volume is a of x times dx gives us volume of one slice. And then we can take the integral to stack up all those slices as they get bigger and bigger and bigger. Nice. Nice. Okay? So now let's get more specific. The volume of the pyramid then will be what, Colton? Yeah, whole thing. Integral from where to where? Right, but we have numbers for those. Specific case. Max and min. What's our min? Yeah, but like, where's this located? Which 0. There we go. 0 on the x-axis. So we're going from 0 to 3. Good, very good. You worked through it. Instead of a of x, well, what expression can we use for the area of this? X squared, right, because it's x and x. Hey, Jonathan, welcome to calculus. Hope we don't mess with your mind. Okay, so now we have x squared dx. So that's the area of the slice face times the thickness of the slice gives us a volume. Okay? And so far you're not impressed, I can tell, but you will be soon. Okay, so now the volume of the pyramid equals, all right, let's do our integral, our definite integral. What do we got? Thank you. X cubed divided by 3. Evaluated from 0 to 3. Or a lot of people say 1/3 x cubed. Same difference. Some people just feel better and warmer and fuzzier. Doesn't matter. Evaluated from 0 to 3. No need for plus c, Derek, because it's definite. Okay. Now, so then we get our volume equals what? Alex, you're up. Go the other way around. Do the 3 first. No, you're working too hard. You had it right before, but you just did the 0 first. And traditionally, we want to do the top one first. Okay. You don't need any over at all. But you had the right idea. It's 1/3 x cubed. So then let's put in this upper limit of integration into x. Okay, and then what, Alex? Waiting time, Mr. Hale. Excruciatingly painful, especially when you're starting out. You don't want to wait. But increased waiting time is really good. Okay, what you got? You're up. Time's up. Well, we're going to go minus 1/3. What's x in this case? 0 to the third. And a lot of people don't bother with this, not mentioning names. Eric. But it's really important to remember there are a lot of cases where this 0 will produce a result. Okay? You can't just say, oh, it's 0, so we're going to ignore it. So I like to write it out, even though it seems tedious. So what's 1/3 times 3 to the third? 9 minus 0. The volume equals 9 units, meters cubed. Okay, now are you impressed? Isn't that as cool as can be? 9 meters cubed, 9 meters cubed, totally different method. I'm thrilled. Jeremy, you vile creature. No! This is great. This is perfect. This is wonderful. Okay? Tom, congratulations. Who else? Derek, Tom, Mo are all singing today. So we're going to text you now and tell you tonight to watch this. It's okay. And Jacob, we're going to text you hopefully and remind you to watch this. And just to let you know, because of time constraints, we're skipping ahead to 8.1. But we do plan to read through those sections about approximating and improper integrals. But as I shared with Johnny earlier, improper integrals are a BC topic. So we're not going to deal with that unless we have time, which right now we don't. Okay, that's all we have. Questions? Pretty cool. Gotta love it. I'll tell you, it just gets better and better. You start doing those slices and those washers and those discs, and whew, it's beautiful. All right, that's all.